Hello everyone, my name is Xiang from Institute of Software Chinese Academy of Science. Today I'm very glad to be here in USENIX Security 2024 to present our paper Evolve in Shifts Closing, Practical Black Box Adversarial Attacks for Evading Learning-Based Windows Malware Detection in the Wild. As we all know, malware remains one of the most serious security threats in our digital life. It normally performs various malicious activities like stealing sensitive information on computers. Since the Windows operating system is widely used all over the world, Windows has become the primary target of malware attackers. According to the statistics from AIoT, over 19% malware samples are Windows malware, much more than other operating systems like Android, Linux, or Mac OS. To defend those malware attacks, there are two major kinds of malware detection, that is static analysis and dynamic analysis. Since dynamic analysis usually requires a sandbox to execute malware, this method is very time and resource consuming, making it less ubiquitously deployed. Therefore, in this paper, we mainly focus on static analysis-based Windows malware detection, and it can be further divided into two categories, including signature-based malware detection and learning-based malware detection. Due to the excellent and promising detecting performance, it is reported that more and more mainstream antivirus products like McAfee are incorporating learning-based malware detection as a pivotal component in their security solutions. Considering the widely usage of learning-based Windows malware detection in both academia and industry, one later but important question is, how about the security risk of learning-based Windows malware detection, especially when faced with adversarial attacks? To this end, we first present our threat model in this paper, targeting at the learning-based Windows malware detection F. The primary goal of our adversary is to generate adversarial malware such that it is not only misclassified as goodwill, but also preserves the original semantics. For adversary's knowledge and capability, we follow the classic black box adversarial attacks. That is, the adversary has no prior information on the target system, except for the predict label, along with or without predict probabilities. Furthermore, to ensure that realistic adversarial malware files can be generated, the adversary can manipulate the Windows executable files. In terms of this threat model, we specifically identify two key challenges that need to be addressed if we want to propose a practical adversarial attacks. The first challenge is how to generate the adversarial malware files that not only maintains the same semantics as the original ones, but also remain less noticeable to possible defenders. The second challenge is how to efficiently search in the vast and discrete space of malware under the black box settings. To address these two challenges, we propose a practical adversarial attack framework, namely MARGAZE. MARGAZE mainly consists of three parts, and next we will introduce each part in details. The first part is adversarial transformation preparation. It first represents the input Windows malware as the control flow graph CFG, and then employ a novel semantic preserving transformation, namely call-based redividing. This novel redividing transformation can manipulate both the nodes and the edges of CFG, making it less noticeable compared to previous adversarial attacks. To be detailed, call-based redividing first find all available basic blocks that have the call instructions and then select one call instruction in the basic block V as the dividing line. That means the original basic block V can be redivided into three basic blocks. In addition, to make it less noticeable, we can further enrich this middle basic block by injecting semantic nums into it. Based on the redividing transformation, generating adversarial malware file is equal to optimize a sequence of transformation that can step-by-step transform the original malware into the adversarial malware. Here, each transformation TI is an atomic call-based redividing and involves two decision-makings. The first decision-making is to select one from all available call instructions to be redivided, and the second is to determine the proper semantic norms to be injected. To optimize this sequence in an infinite and discrete space under the black box setting, we employ the Monte Carlo tree search-based optimization. More details can be found in our paper. The third part is how to reconstruct the final adversarial malware file. For each transformation in the sequence, Malware patches the original malware file by injecting the original basic blocks into snake space or into a new section, and then adjust other fields in the header information. It is noted that all those patches are obey the specification of Windows executable files. The right finger here shows that after applying two core-based redividing transformation to the knockbit3 ransomware, the generated adversarial knockbit ransomware can successfully evade 3 SOTA learning-based detection in our evaluation. To evaluate the effectiveness of malware, we first introduce some of evaluation settings in these slides. For the dataset, we employ a large wide dataset containing hundreds of thousands of Windows malware and goodwill, and further split it into 3 disjoint sub-datasets of training, validation, and testing. For the targeted system, we totally employ 2 kinds of targeted system. The first is the learning-based Windows malware detection systems, including Malgraph, Magic, and Malcom. Another kind of targeted system is 5 widely used antivirus products. To compare, we also employ 2 kinds of baseline attacks. The first is 2 adversarial attacks against Windows malware detection, and they are MMO for HCCS and SIL for TDSC. The second category includes 3 obfuscation tools, and they are UPS, Web Protector, and Enigma. The first research question we want to evaluate and answer is, what is attack performance of malware against the SOTA learning-based Windows malware detection systems? It is observed that for baseline adversarial attacks, MMO shows inferior attack performance on all targeted systems in both scenarios, while SIL shows obviously higher attack performance on Magic. This is mainly because SIL is specifically designed to attack Magic, which purely built on CFG. For baseline obfuscation tools, all those obfuscation shows inferior attack performance. Finally, when comparing our malware with all those baseline attacks, we can find that malware achieves the best attack performance on all targeted systems in both scenarios with a very high attack success rate of more than 95% in most cases. The second research question we want to evaluate is, does adversarial malware generated by malware still maintains the original semantics? In particular, we define a new evaluation metric called semantic preservation rate (SPR). As we can see from the equation of SPR, the core is to judge whether the adversarial malware has the same semantics as the original malware. However, due to the inherent complexity of executable software, there is no exact solution to judge it. Therefore, in this paper, we present an empirical solution by connecting and comparing the 2 API sequences when we run both the adversarial malware and the original malware on the same sandbox. For the evaluation result in the table, we can observe that for MMO, less than 15% of adversarial malware can preserve their original semantics. However, malware achieves the best utility performance with over 91% of adversarial malware can preserve their original semantics. The third research question we evaluate is, to what extent does malware evade existing commercial antivirus products? To answer this question, we empirically evaluate malware against 5 antivirus products. From the evaluation results, we can observe that apart from Kaspersky, malware achieves over 13% attack success rate against the 4 antivirus products. This actually presents real potential security concerns to real-world users. We also observed that malware only need to modify a few basic blocks in the original malware to evade antivirus products. In particular, for McAfee, Commodore, and ClaimAV, over 90 adversarial malware only need to modify one basic block. For the others, they only need to modify two basic blocks. Finally, to sum up in this paper, we want to understand and evaluate the security risk of existing learning-based Windows malware detection, and we thus present a practical black box adversarial attacks called Malgas. Malgas is the first to apply a code-based redividing manipulation towards the CFG of Windows executables, which not only manipulate the CFG's nodes but also its edge. Evaluation also shows that Malgas can not only evade SOTA learning-based Windows malware detection, but also can evade 5 commercial antivirus products. Finally, we will share our code to academic researchers. Thanks for listening, and I'm ready to answer the questions.